In this section, we will look at an extension of the remainder theorem called the factor theorem. It's a powerful tool that we can use to solve equations that involve higher degree polynomials, like this cubic, which has an x cubed term. You're probably a little stumped as to how we can go about solving this, so let's take a step back to something that's hopefully more familiar to you. Let's take a look at a lower degree polynomial equation involving a quadratic, which has an x squared term. Can you think of a way to solve for x? We could use the quadratic formula, but for our purposes, we're more interested in solving by factoring. Once we've factored this trinomial, we can identify the values of x that will cause the expression to evaluate to 0. To factor the trinomial, we look at the leading coefficient, which is the coefficient on the x squared term, and multiply it with the constant term to give us our so-called magic number. 2 times 5 gives us 10. Now we look to the coefficient on the x term. We're looking for two numbers that multiply to give us our magic number, 10, and add to give us the coefficient on the x term, negative 11. We could write out all the factor pairs of 10, both positive and negative, and sift through until we come up with one that works, but I'm going to jump right to negative 1 and negative 10. Now we will use this factor pair to split the negative 11x term into two smaller terms, negative 10x and negative 1x. Note that the order of the negative 10x and negative x terms could be swapped, and we would still come out with the same answer in the end, albeit with slightly different work to get there. Now, from the pair of terms on the left, we pull out the greatest common factor, which is 2x, since both coefficients are even and both terms have an x. This gives us 2x times x minus 5. From the pair of terms on the right, we pull out the common factor of negative 1. Which leaves us with negative 1 times x minus 5. Notice that the expressions in both brackets are the same. This is a sign that we're on the right track. The last step to complete the factoring is to write the coefficients on the matching brackets in their own set of brackets and multiply by what was in the matching brackets, giving us 2x minus 1 times x minus 5. From here, we have fully factored the quadratic, and we can determine the values of x that will set each factor to 0 and solve the equation. Let's start with 2x minus 1. We set it equal to 0 and begin solving for x. We add 1 to both sides to get 2x equals 1, and then divide by 2 to get x equals 1/2. Doing the same with the factor of x minus 5, we add 5 to both sides to get x equals 5. The two values of x that cause our polynomial to evaluate to 0 are 1/2 and 5. These are the roots of our polynomial. Take note of how they are related to the factors of the polynomial. Look at the factor of 2x minus 1, which has the form bx minus a. Its corresponding root is a over b, or 1/2. The factor of x minus 5 has the form x minus a, and its corresponding root is a, or 5. Hopefully this has been a nice refresher on how to find the roots of a quadratic function by factoring. But what if the function is cubic, or quartic, meaning degree 3 or 4? Look at this example from the beginning of the video. We want to apply the same approach of factoring to find the roots. Can you think of a way to factor it? Probably not yet, as this is where knowledge of the factor theorem becomes necessary. This cubic actually does factor quite nicely down to x plus 1 times x minus 2 times x minus 7. Remember that we observed factors of the form x minus a correspond to roots at x equals a, so the three roots from these three factors are negative 1, 2, and 7. In the next video lesson, we're going to look at the factor theorem, which will give us the tools we need to factor cubics like our example here. Stay tuned for that.